And first of all, I would like to thank the organizers for the invitation. So let me first mention that this is joint work with Michael Hoff. So if you can't read something, please don't hesitate to ask. It seems that I have a very bad handwriting on this whiteboard. So first of all, let me explain this notation here. So this means that I do not care too much about the actual map to P1. So W196 consists set theoretically of pairs CL, where C is an element of MG and L is a point in the Brill-Noether variety of C. Sorry, yeah, this was. Thank you. So from time to time it happens that this line bundle here has precisely two sections, and in this case I will associate this line bundle L directly with a one-dimensional linear series of degree k and write G1k for this. Okay, so my talk is basically divided into two parts. The first part consists solely of curve stuff, and the second part connects this with K3 surfaces. So I'm going to start with the first part, and this is going to be about what I and a few others like to call relative canonical resolutions. Okay, so the situation is the following. I have a curve C in PG minus 1, and by writing it this way I mean that it's canonically embedded. So canonically embedded curve of genus G with a base point free G1k. Okay, and what I can do now is I can consider the variety X, which is the union of the linear spans of the divisors in this one-dimensional linear series. And this turns out to be a rational normal scroller. And we also know the dimension, so the dimension of X is precisely k minus 1, and the degree of X is G minus k plus 1. More generally, scrolls occur in the following way. So X is the image of a map which I will call J from some projective bundle into this space here, the projectivized space of sections of OPE of 1. And PE is a projective bundle over P1, and the bundle E itself is a rank k minus 1 bundle on P1, therefore it splits, and I call the twists EI. And I know that. So I want that the EIs are greater or equal than 0, and the sum of the EIs is precisely the degree of X. Okay. So for the most stuff I'm going to talk about today, it doesn't matter if I consider X or P of E. In the case that all these EIs are strictly greater than 0, this is an isomorphism, and if not, this is a resolution of singularities. But as I told you, it doesn't really matter for my talk what I will consider. Okay. We already saw this in one of the last two talks, but I'm going to use slightly different notation. So the Picard group of this guy here is generated by the hyperplane section H and the ruling, which is the pullback of the hyperplane section of OP1. Of P1, sorry. And here is a small fact. So if I take C and G1K in the Hurwitz space to be general, then this bundle E associated to the scroll swept out by this G1K is what we call balanced. And this means that the maximal difference between EI and EJ is smaller or equal than 1. And I mean, knowing this, you know precisely how this bundle E looks like in the general situation. And this fact here follows in fact from Theorem of Balico. Okay, what we want to do now is we want to resolve our canonical curve C on the scroll. This means in terms of OPE modules. So and we have the following theorem due to Schreier from 86. So C inside PE, so the setting is as before. I have a curve C canonically embedded with a base point free G1K. And this guy here is associated to this G1K. And this has a free resolution of the form 0 OC OPE. Then I pull back some bundle on P1 and twist this by -2. Pull back of some bundle N2, twist it by -3. Then it goes on with linear twists until I reach pi upper star nk -3, twisted by -k plus 2. And the very last term is pi upper star of nk -2, twisted by -k to 0. Okay, so I should tell you what these bundles Ni are.
What was the last twist there?
Sorry?
What was the very last twist?
K. Nk -2 twisted by -k. And pi upper star of Ni has the following form. It's a direct sum. J equals 1 up to beta I, depending on this I. O, P, E, A, J, I, some integers depending also on I, twisted by R. So the actual bundle Ni looks basically the same, just forget about the R and substitute PE with P1. And these beta I's are also known, and this is why I keep my notes. So these are k divided by I plus 1 times k minus 2 minus I times k minus 2 choose I minus 1. Okay, so we basically know the ranks of these bundles here. And we have this mysterious AJIs. And this complex has a feature that it's self-dual. So I can dualize this complex, and up to twist, this looks precisely the same. And we not only know the ranks of these bundles appearing in the so-called relative canonical resolution, we also know the degrees. The degrees of these bundles Ni, which is just the sum over this AJIs. So, and as for the scroll bundle E, you can ask, if in the generic situation this resolution is balanced or not. And people have asked this question and have made some progress. So this is widely open, but this is known to be true for k smaller or equal than 5. The very first bundle appearing here is known to be balanced if G is much bigger than k. So that the first bundle is balanced if G is much bigger than k is due to Gabriel Boujokas and Anand Patel. And together with Michael Hoff, we considered the case of this bundle Ni when the Brunner number is positive and showed that it's most of the time not balanced. And we could give a precise statement, this bundle N1 has the following form if and only if certain conditions are satisfied. And out of the study of this so-called relative canonical resolution, we somehow got into the project I'm going to talk to you today, where we considered curves where the first bundle is balanced and the second one is not. And the first case where this appeared was precisely the case of genus 9 curves together with the G16. So before going to genus 9 curves, I would like to make a small example. So if I take a general element in W185, then C inside the scroll has a resolution of the form 0 OC OPE OPE twisted by minus 2h plus R to the 4 plus OPE minus 2h. Okay, that's it. O minus 3h plus 2R plus O minus 3h plus R to the 4, and I omit the very last term. Okay, this is a particularly nice case because by the Buchsbaum-Eisenbart structure theorem for codimension 3, it is known that the map psi here is skew-symmetric and the 5 Pfaffians generate the ideal of C on the scroll. So this is a case which is completely understood. And we can also associate Betti tables to these bigraded resolutions, and I will do this by example. So in this case, my Betti table will look like 4, 1, 1, 4, 1. So I have to declare what the linear maps are, and I want the linear maps to be the maps which have entries in H0, H minus R. This is just a convention, but this is the way I want them to be. Okay. So let's get to genus 9 curves. So this will be the second part. It's genus 9 curves and K3s. And we have the following proposition, which we will call existence. That's basically an extended example of what we computed. So part A, there exists a point CG16 in W196 such that C is smooth.
Can I ask you a quick question?
Yeah?
So how does this resolution, so what's the interplay between the canonical embedding the G15 and this resolution right here?
You could resolve all the guys appearing in this resolution by OP G minus 1 modules, and then an iterated mapping cone would give you a resolution, and minimizing this would give the actual minimal free resolution. So that's the interplay, and that's what Frank did in his PhD thesis, but today we stick to the resolution on the scroll.
Where's the G1? How's the G1?
The G15 determines the length, and the G15 determines that the curve inside the scroll has codimension 3. And therefore, I get that this map here is skew-symmetric, and the Pfaffians generates curve. Okay, unfortunately, we have no longer structure theorem for codimension 4, which is the case for genus 9 and hexagonal curves. So the situation here is not completely understood, but what we can say is that there exists a point such that C inside PE has a resolution of the form so O minus 2H plus R to the 6 plus O minus 2H plus nothing to the 3, O minus 3H plus 2R to the 2, plus O minus 3H plus R to the 12, plus O minus 3H to the 2. So is this correct? I hope so. Yeah. And then here's the point where the duality kicks in. So we again have O minus 4H plus 2R to the 3, and here we have this term to the 6. Okay, so in particular, we see that the second bundle appearing in this relative canonical resolution is unbalanced, so that's what we found. And just to repeat, I will write down the Betty tally. So we have 1, 6, 3, 2, 12, 2, 3, 6, 1 in this case. Okay, this is part A, and part B is where the case 3 comes in. So the statement is the following. There exists a syzygy, let's call it S, from O minus 3H plus 2R to O minus 2H plus R to the 6, whose syzygy scheme defines a case 3S such that the Picard group of S contains the hyperplane class, which is just the hyperplane class restricted to H, our curve C, because it's a syzygy scheme, and I will explain what this is in a minute, and a class which we call N, which is the restriction of the ruling to our case 3 surface S. And the intersection matrix looks as follows. Let's call this H. And we have a 14 here, 14 here, 5, 6, 0, 16, and of course this is symmetric. So let me explain what this means. So our curve H is represented by a genus 8 curve on the surface. Our curve C is our genus 9 curve, canonically embedded. And then we have this class N, which is given by an elliptic curve. And this elliptic curve cuts out our G16 on C, which is no surprise, but it also cuts out the G15 on our genus 8 curve. So that's the situation. And now I'm going to explain very briefly what a Syzygy scheme is, at least in this situation. So let F1 up to F6 be the generators of C corresponding to the O minus 2H plus R to the 6th term. And in... Yes. Thanks. And in this very special situation for genus 9 curves with the G16, we know that the space parametrizing the entries of this syzygy here is 4-dimensional. Yeah, this can be computed. So therefore, base change gives us that S is basically of the form S1 up to S4, 0, 0 transpose. And the same base change gives us new generators F1 prime up to F6 prime, such that this is still a syzygy for these new generators. So F1 prime up to F6 prime times S1 up to S4, 0, 0 transpose is 0. And the syzygy scheme defined by this syzygy S is just the ideal generated by F1 prime up to F4 prime. So that's it. And this guy defines a case 3, but let's say it determines a case 3. The actual case 3, for the actual case 3, you take the variety defined by these 4 elements here, and then you saturate with the vertex of the scroll, which is in this case 0-dimensional. So this gives you a case 3 surface, but it's a well-defined procedure which gives you the case 3. Okay, so yeah.
Is something which is particular to the geometry here, or can you deduce it from any data diagram like you have?
This is something which seems to be very particular, but we have other cases where similar things happen. Yeah, but no one expects that a genus 9 curve lies on a genus 8 case 3. But it seems to be the generic situation. So that's what we're going to show. Okay. So let's talk about case 3 surfaces, or at least their moduli space. And I'm writing down everything for this lattice H we have here, but everything holds in a much more general situation. So the definition and the theorem is due to Dolgachev. And what he defines were so-called lattice polarized case 3 surfaces. So H polarized case 3 is a pair S phi, where this is a case 3, and phi is a primitive lattice embedding from H into the Picard lattice of S. And the theorem part is the following. The moduli space FH parametrizing isomorphism classes of lattice polarized case 3s exists as a quasi-projective variety. and it has dimension 17 in this case. So this number has to be read as 20 minus 3. It's always 20 minus the rank of the letters we are considering at this moment. Okay. Of dimension. So this guy is not really irreducible, but it could have two components, but it's the case that if we know one component, then we automatically know the other component. So this is a fact which comes from the construction of the space, and therefore we don't have to bother about the irreducibility in this case. Okay, we need a little bit more notation. So fixing a basis element big H of small h, we get a new moduli space FH8, which is a finite cover of FH. So you should think of this guy here, or the elements of this guy, as big H polarized K3 surfaces, which for which small h is a sublattice of their Picard lattice. Yeah, that's yeah. Okay. Okay, last we define a guy which I call PH8, and which consists of pairs S, C, such that S is a K3 in FH8, and C is a curve in the linear series C on S, which I want to be smooth. So this is a tautological P9 bundle over FH8, and this is the guy we want to consider. So our main theorem is the following. The map, or the morphism, phi from PH8 to W196, sending a pair SC to C together with OSN tensorized with OC, is dominant. So furthermore, over an open subset of W196, the fibers are isomorphic to P1. Okay, since we know that this space here, W196, is unirational, and knowing that over an open subset we have fibers isomorphic to P1, this theorem gives us in particular the unirationality of this guy here, and the tautological bundle over FH8. So this is what we want to show. So we need a little bit of preparation. So lemma 1. Let S C be a general element in pH8. Then two things hold. So first part L, which I defined to be OS n tensorized with OC, defines G16 on C such that S is contained in the scroll swept out by this G16. So this is relatively easy to see. And part B, S inside the scroll has a relative canonical resolution of the form zero OS OPE O minus 2H plus R to the 4 plus O minus 2H O minus 3H plus 2R O minus 3H plus R. And I again omit the last term because we already know this resolution. This is precisely the resolution or the shape of the resolution of a general genus 8 curve together with a G15.
It's your handwriting, yeah, I think. Who's the twist on OS for when you're defining L?
N. The elliptic,
That was
the elliptic curve. So, such that this guy has a chance to be the G16. Okay. So, the examples which I wrote on the whiteboard at the very beginning actually is part of the proof of part B. So having this larger scroll PE inside PG minus 1, I can intersect with the general hyperplane. What I get is a smaller scroll which is contained in this hyperplane. And it can be shown that the genus 8 curve inside the scroll, inside the surface S, which now also lies in the smaller scroll, has a resolution of generic shape. So this is, yeah, that's basically how you prove this. Okay, so what does this buy us? Now we know that if we have a generic point in pH8, then C inside the scroll, which is defined by this G16 here, has the form (163) A 16 minus 2A A 36 for some A strictly greater than 0. So in particular we know that if we have a general element here, then the relative canonical resolution is unbalanced. Okay. The nice thing is, knowing the resolution, we can also say something about the fiber dimension of this map phi here. So this will be the next step. Actually, I forgot to tell you why people actually care about balancing. But it's quite natural, and Most of you might know this from the moduli space, where you can construct so-called causal divisors. You can look at subspaces in your moduli space where the resolution has a strange shape. And this might give you, if you're lucky, a codimension 1 subset. And these divisors then are used to study the geometry of your moduli space. So this is why people are also interested in the balancing of the relative canonical resolutions, because they want to understand the Hurwitz space. Yeah. So I forgot to tell you that. Okay. So lemma 2. If I have a curve, so CG15 in W196, such that my curve C has a resolution of the form 6, 3, A 16 minus 2A A 3, 6, yeah, as it's given here, then the fiber dimension of phi over CG15 is at most, G16 is at most A minus 1 dimensional. Okay, so how does this work? This is true because it can be shown that this part here of the resolution of the K3 surface on the scroll determines the surface uniquely up to isomorphism. Yeah, that in fact follows or can be deduced by a theorem of Frank Schreier, and it's not that hard to see. Yeah, what you basically do is you resolve this linear map by a causal resolution, and one term in this causal resolution parameterizes skew-symmetric 4x4 matrices, which are these maps here. And the map before that step gives you the action of the other columns on this 4x4 matrix. So, okay. Now we know that if we have a strange, unbalanced relative canonical resolution, then we can bound the fiber dimension. And basically these are all the ingredients we need for the proof of our main theorem. So, let's prove the dominance part. So therefore, note that the map PH8 to Z, sending a point X to the local dimension at X of phi inverse of phi of X, is upper semi-continuous. Yeah, this is true because this is a nice variety. So in the next step, our existence proposition gives us an image point. Let's call it CL. And our lemma 2 now says that this dimension here at the point CL of phi inverse of phi of CL is smaller or equal than 1. And the semi-continuity now gives us this in an open subset. Such that dimension of x in x of phi inverse of phi of x is smaller or equal than 1. Okay. Now it's time to count dimensions. So this is certainly 17 plus 9, 26. And this is certainly the dimension nx of phi inverse of phi of x for this x in U, plus the dimension of the closure of the image. Yeah? Okay, and this is certainly smaller or equal than 1 plus the dimension of W196, which also turns out to be 26-dimensional. And since this guy here is irreducible, we get that phi of U is dense in W196. Okay, so this proves the dominance part, but from the dominance it can be shown that, or it is basically clear, that the situation of our proposition where we just stated the existence of one case is actually the general situation. That the proposition describes the generic situation, and what follows is that pH8 is birational to let's call this W196 tilde, which consists of triples C, L, S, where CL are in W196, and S is one of the syzygies I can choose. Is an O minus 3H plus 2R to the 2, which over the open subset of W196, where the resolution has generic shape, is obviously a P1 bundle over this open subset. So therefore we get this in particular part of our theorem, which states that over an open subset the fibers are isomorphic to P1. So I actually planned with 50 minutes, so now I can try to answer Gunnar Floistad's question on if this is something special. So what I'm going to talk about now is just what the Macaulay 2 experiments gave us.
Can I ask one? I just wanted to leave my question out there too. Is there an obvious reason why the resolution of OC is an OPE module is also Borenstein? There's this symmetry effect that it can.
Oh yes. I mean you always have a self-dual relative canonical resolution.
But over OPE.
Yeah, this is always true.
It's over OPE.
So there is a whole class of curves together with line bundles which seem to have a similar property. And what these are curves C together with a G1, G minus 3, where this is a genus. So, okay, let's, we have already seen the case C genus 8 with a G1, 5. And in this case, we had a hyperplane section of the Mukai variety G26, which parameterizes genus 8 case resurfaces. So this was a Betti table of the form here. Then we had the case G of genus 9 with a G1, 6. And we have seen that Syzygies here give us a case resurface. And we can keep this going on. So it seems that for C general genus G with a G1, G minus 3, the Betti table looks as follows. We have something here, and our previous work ensures that the first bundle is balanced. And then we have, now I have to compute, G minus 3 minus 4, G minus 7 here. And some other terms which we don't know. And what happens if we take the Syzygy scheme in this relative linear strand is that we get higher dimensional varieties which also have a genus 8 case resection. So this is what the experiments show us. So for genus 10 with G17, I get a threefold which contains the curve C, and the hyperplane section is a K3. But all these classes, C is no longer a divisor on this n-fold. So the whole theory we applied in this situation will no longer work out. It's also not clear what happens if we get over the dimension of G26. We don't know because we cannot compute it. We expect that it might be a cone over the G26 or something like that. Yeah? But so this is a very big question mark why this is true. This number here always increases by 1 and basically describes the dimension of the variety I get when I take the Syzygy scheme. And it seems to be a lot of interesting geometry involved in this particular case, but we don't see it, not yet. Okay, these are precisely my 50 minutes. Thank you.